I'm a senior data scientist at Diagnostic Robotics, and today I'm going to talk about artificial intelligence solutions in healthcare, and especially how we use NLP aspects in medical records and how we model NLP in our datasets. So a little brief about our company. Diagnostic Robotics was founded 3 years ago by Jonathan Amir, Dr. Kira Rodinsky, and Professor Moshe Shoam, with the goal to build artificial intelligence solutions to make healthcare more effective and efficient. And we use different types of data sets. We use emergency room data. We have tens of millions of visits in the emergency room. We have HMO data, tens of millions of visits. And we have claims data of insurance company with all the transactions of the patient timeline, and with all the codes of diagnosis, procedures, and medications. So the company first was founded in order to solve the problem of the emergency department, where we can see three main problems in the emergency rooms in the world. One of the problems is overcrowding. The second problem is medical errors due to stress and pressure in the emergency rooms. And the third one is a clinician shortage. And if we look all over these problems, this cause for 8 hours waiting time in China, for example, and which is very long wait time. And a research was conducted and found that the annual emergency department visits are growing faster than the population itself. Here you can see the growing of the population in the red line, and the annual growing of the emergency visits in the department of the emergency is growing faster. All these reasons led the company to build AI solutions in the emergency room. So we put our system in the emergency room in Israel, as you can see here in the pictures, and we let the patients in the emergency room to fill our patient questionnaires, and then we can use these answers in order to triage, in order to have a triage system and to put all these answers in a medical dashboard to the doctor to make the process faster and more efficient. And so we began with that system in the emergency departments, but then we saw that we can use this system in a full line of home-based triage system and in a population health solutions. So now we have two main products, two main problems that we want to solve. One problem is to build AI augmented home-based triage. So we have the applications where the patient can fill our questionnaires from home. He didn't have to come to the emergency room, and that's how we save time and money of the patient in waiting in the department, in the emergency department. And after he fills out our questionnaire, we can transfer our recommendation, AI recommendations, treatments, diagnosis, resources to the doctor that treats the patient, and make the whole process more effective, and help the physician to treat the patient in the best way. The other type of problem that we want to solve is to predict population at risk, meaning this is a proactive product. We want to recommend on patients that are at risk or potentially at risk, like CHF patients, like obesity deterioration or behavioral health deterioration. And we want to find this kind of patient before their situation becomes worse, and we can help the care managers in the US to find and recommend them intervention programs to make their situation better. So let's talk about our first product, our first problem that we want to solve. And so as I mentioned, we have the patient that suffers from headache or chest pain, and he fills out our questionnaire, our application. After he finished the questionnaire, our AI system is working, and we extract to a doctor dashboard our medical summary, our treatment recommendations, and diagnosis to consider recommendation, which help the doctor to make better decisions. So why to use NLP in this type of product, in this type of process? So in order to build the AI mechanism that in this process, we need millions or thousands of questionnaires answers, which we don't have because we didn't have enough questionnaire yet. But we do have millions of medical visit texts. We can use these data sets, these textual data sets, and extract the answers to the questions from this text, and use it in order to build the ML models. So I will talk how we do it and how we extract from medical visits text concepts, medical concepts, and how we use deep learning models in order to do that. And next, I will show you some examples of diagnoses that we predict using this system. Okay, so the main idea here is to take the unstructured data, all the textual data, which is unstructured, and extract concept from this text. For example, we can extract symptoms, cough, chest pain, fever. We can extract conditions of the patient, okay? And from unstructured data, we can get structured data metrics, okay? Where we have in the column the patient, the visit case, and the vector of the visit case include all the concepts that are mentioned in this visit. So if we have the cough mentioned in this visit, we will put a highlight in this vector, and this vector will represent the visit with all the concepts that are mentioned in it. Next, we will use these metrics to train our ML models. So let's take a look on this example. So this is the text we have. Okay, we want to extract that the patient have a condition of psychiatric illness. Okay, we want to find the medication that the patient is treated with. We want to extract the symptoms that the patient suffers from, for example, headache. But except from finding the symptoms itself, we want to find the attributes that describe this symptom. So in this example, we can see that we have the location of the headache, which is anterior. We have the feeling, the sensation of the headache, which is heavy. And we have the duration of the headache, which is several months. All of these attributes describing the headache, and we want to include these descriptions in our model. And next, we want to find the value of the concept. We want to find if fever is mentioned in a negative manner or in a positive manner. In this example, without fever, because of the word without, we know that the concept fever is negated. Some visual disturbance is negated. Headache is mentioned in a positive manner. Okay, so we build a pipeline to extract all the concept from the text. We have a lot of classifiers to do that, but I will focus today on two of our main classifiers. And one is the entity relation classifier, and the second one is the negation classifier. So let's take a look on the entity relation classifier. So the main goal here is to find the relationships between the symptoms and the entities that describe this symptom. So if we have headache and chest pain symptom, we want to describe these symptoms using the location, the sensation, the duration, and their values. The location is anterior, the sensation is heavy, and the duration is few days. And if we have this sentence, the patient suffers from headache and stabbing chest pain, we want to find that the stabbing entity is related to chest pain, but it's not related to headache. We have stabbing and headache in the same sentence, but in this scenario, stabbing is related to chest pain, and we want to describe stabbing. We want to describe chest pain with the word stabbing. So there are different approaches to do this. And one of the approaches is to use dependency tree. Dependency tree is NLP a mechanism to find a dependency between words in a sentence. So we can use it in order to find that stabbing is related to chest pain and not related to headache. Another approach is to use feature engineering to get statistical measures of the words in the text. For example, the frequency of the words, the co-occurrence of the two words in the text, PMI measures, and to use model to find using these features if the two words are related or not. And the last approach is to use end-to-end deep learning framework in order to train a model that says if the two entities are related or not. And the third approach is more common in the recent years, and it outperforms the other approaches. So we will use it. In order to do this relationship model, we used a Google model, which was published in 2019, and they presented in the paper 6 main architectures to do that. I will focus in one of them, which got the best results in the paper. So the main idea here is to use a deep learning classifier to classify if two entities are related or not. So we have a deep learning model with a softmax layer with the label of 0 if the two entities are not related, and with label of 1 if the entities are related. And we can use a binary classifier or a multi-class classifier if we have the type of the relation, and we can use the type of the relation as for the classification. So the main idea of the problem is to use markers. How we use the top markers? We have a start marker for the sentence, CLS. We have end marker for the sentence, separator, which is a very common way to in NLP to mark the sentence. But except from these two markers, we have markers for the entities to emphasize the entities in the text. So we have entity 1 with the E1 as the first marker, as the start marker for entity 1, and /E1 as the end marker of entity 1. Same we have for entity 2. We have E2 and end of E2 to define the start and end markers of entity 2. So we have a modified sentence with the markers of entity 1 and entity 2, and we can insert this sentence into a deep transformer, into BERT or to a bidirectional LSTM, and to take the contextual embedding of the start marker of entity 1 as representing entity 1, same as we represent the entire sentence with the start token of the sentence. We can use the start token of entity 1 to represent the meaning of entity 1. We take the contextual embedding of entity 2, of the start marker of entity 2 as well. And we concatenate them. We concatenate them into one vector, and this vector represents the relationships between the two. Then we can insert this vector into a dense layer and a softmax to get the classification of the two entities, which is related or unrelated. So using this method on our dataset gave us very good results. We got a ROC AUC of 96%, and we got 81% of precision recall AUC. And what is very interesting to see is that we compare the model to two baselines for headache and chest pain attributes. And we found out that if we take the components of headache that are mentioned in the same text or in the same sentence, we got 51% F1 score. But the model gives us 72 F1 score, which is absolutely 20 more points to the F1. So it's a big improvement. And the baseline here is to find to declare components, triads components that are related if they are mentioned in the same sentence. So we see how the model outperforms these baselines. So this is the first model that I want to share with you. Another model is the negation classifier. So what is the negation classifier? If we will take a look on these examples, we have without fever or visual disturbance. So the concept fever is negated because of the word without. Visual disturbance is negated as well because of the word or, that continues the negation of the word without. The patient does not mention a fever, but mentions a cough, so does not makes fever negated, but the word but cancels the negation for the word cough. We have multiple negation that becomes positive. The patient denies fever, vomiting, nausea, and blurred vision. All of these concepts, fever, vomiting, nausea, and blurred vision, are all negated, but the word dizzy is positive because of the word feels. So we would like to find for each one of the concepts what is their value. Is it positive value or negative value? In order to do that, we use a masking mechanism. Masking mechanism helps us to deal with two issues. One issue is to tell the classifier which one of the words in which one of the concept in the sentence is now on focus. So, for example, in the first sentence, we want to put on focus the word fever. So fever is now on focus. We use a mask to declare it. Okay, and the label for this sentence is -1 because fever is negated. Okay, so here you can see how we use this masking mechanism in all the sentences for different concepts that we want to put on focus for the different labels. And the last sentence put on focus the dizzy, which is a positive with a positive label. This is first issue that the masking helps us to solve. Another issue is a generalization of the model. The masking helps us to generalize the model because it doesn't matter for us if the word behind the masking is fever, is vomiting, is nausea. It doesn't matter exactly what is the word. What is matter to the model is the pattern of the sentence, and we want to find that denies is coming before the word mask, and this caused the model to say that the masking is now negated because of the pattern of having the denies before this word. So we have this modified input, and we can insert this input into a bidirectional LSTM with attention, and we can use attention mechanism to find the relevant words that help the negation mechanism, like words like denies, like without, we expect to get a high attention score. And we can use transformers like BERT with the input, with the same input, and get the classification of negation of positive per sentence, per concept in the sentence. So after applying this model, we got again a very good result on our data set. We got 97 ROC-AUC, almost 99% of precision recall AUC. This program is we see how it's pretty solved, and we got very good results. So this is two models that we use in our pipeline. We extract all the concepts from the text, and then we build on these features ML models to predict diagnosis. So let's take a look on examples to predict diagnosis. So I will show you the results on very big hospital in Israel, RAMBAM Hospital in Haifa, where we have 800K emergency visits, and 30K out of them are headache cases, where headache mentioned as a chief complaint of the visit. So taking all headache examples, we train a model on the headache samples, and we got result of predicting the right diagnosis in the first top 3 recommendations with 98 accuracy. If we recommend the doctor just the first one, just the first recommendation of diagnosis, we got an accuracy of 80%. So we find out that the best way to help the physician and give him recommendation is to show him top K results of diagnosis. And let's take a look on this example. We have a male, 25 years old, with left-sided frontal headache, stuffy nose, vomiting, etc. And we extract from this text all the concept that I showed you before, and these concepts are inserted into our ML models. And we predicted that these patients in the first top K he suffers from sinusitis with 65% probability. We have relative probabilities as well to define the relative probability regarding the prior for each one of the diagnoses. And we can see the reasonability for choosing this diagnosis in the first place. So sinusitis is in the first place because of the features we found in the text of cold and stuffy nose, headache worsening when leaning forward. And after a real examination, a physical examination of ENT and the CT brain scan, the patient was really diagnosed with acute sinusitis. So this is a true positive case. Another case where we have 35 years old male with sharp temporal headache, with high eye pressure, pain, and lacrimation. And for this patient, we predicted that he has a cluster headache in the first place. If we use the relative probabilities, we found out that he has a cluster headache in the first place, sinusitis in the second place. And the reasonability for cluster headache is the lacrimation and pain or discomfort in the eye that we found in the text. But after a physical examination of a neurologist and the ENT, we found out that the patient was really diagnosed with sinusitis. So this is a case where we found out that we need to use physical examination of the physician in order to determine what diagnosis the patient suffers from. But with our recommendations and reasonability, we help the physician to get decisions and to make the physical examination better physical examination and better decision making. So this is the process for our first product, our first problem that we want to solve, how we extract concepts from the text, use them in our pipelines to predict diagnosis and treatments, and help the physicians in their decision making. Our next product, our next problem that we want to solve is the population health AI solutions. We want to predict which patients are at risk, which patients are potentially at risk, and to recommend them intervention programs and to treat them before their situation becomes worse. So in order to build this kind of models, we use the third type of data we have, claims data. Claims data doesn't include textual data, but it includes all the codes that the patient had in his timeline, from diagnosis codes, medications codes, and this kind of codes along all of the timeline of the patient. And we can use NLP methods to find embeddings of the codes and of the patient. So, for example, we used a word-to-vec embedding method over the codes in the patient timeline, and we found out the representation vector for PTCI for procedure. And you can find here what type of other procedures, other diagnoses, other medications were similar in the embedding space to these procedures. The doctors among you can find their relationships between these codes, between these procedure, diagnosis, and medications. And the main idea is to use this medical code embedding and to represent the patient. Okay, so we begin with the medical codes in the timeline of the patient. We do a clustering of the codes with ATC or CCS, and then we aggregate the embedding of the codes in order to get the representation of the patient. We use an end-to-end deep learning model to predict what patients are at risk or potentially at risk, which patient their situation is going to become worse. And we do that by using the patient timeline. So we have the monthly buckets of the patient. You can see here this matrix is the different month buckets of the patient. Each month is associated with the codes within that month. So we use the embedding codes and get the aggregated embedding for each one of the month. And we can insert this embedding of the month into a sequential or convolutional models, LSTM or CNN, and get the modeling of the temporality of this sequence. And then we get the final embedding of the patient using all the month and codes he had. And this representation is, we use it to predict the final label, which is binary label, if this patient is going to be at risk in the next 3 months, in the next 6 months, and etc. You can read about this research. We published a paper in Nature Scientific Report, and we showed her that predicting preventable hospitalization of patients using this model outperforms logistic regression models. So these are our main two problems that we solve with NLP. One is on text, and one is on medical codes timeline that we use NLP methods as well for this problem. And that's it. I hope you enjoyed the lecture. If you have questions, you're welcome to ask. Thank you.